All right, so let's try this one. So we're going to draw the influence line for the... Well, you know, I don't remember what we were drawing the influence line for.
The positive moment at D.
Positive moment at D.
Yeah, next one.
Okay, so the first thing we have to do is draw the influence line for the moment at D. So the way I like to visualize that is I'll redraw the structure, but at D I'll put my internal hinge. So this is the qualitative technique of Mueller-Breslau. And in that case, we'll look at our positive moments being applied here. So what's going to happen? This point should move up, and then you should see a structure that looks something like that. Everybody follow that?
If you said just found the moment at D, how would you know whether it would be negative or positive?
We don't.
What to start with?
We don't know yet. We're going to check both cases. So this is my influence line then. So my influence line for the moment at D is going to look like this. So I'll try to draw it a little more to scale. So just to help me, I'll just transcribe these points down. And then it's going to look exactly the same as before. Except now we have real dimensions. So this is going to be 5 feet, 5 feet, 5 feet, and 10 feet. Now I need to get one of these values. So which one do you want to work? I remember trying to find I said C. This is the moment at D here. So I think I'm going to use this case. So what I want to do now is I want to rework the problem. So now that I have the qualitative shape, I want to get the quantitative values. So there's my beam. But now since I'm interested in this position, that's where I want the unit load. So again, my dimensions are 5, 5, 5, and 10. Everybody see that? So I want the moment at D, which happens to be this point, when the unit load is at D. So if I cut the structure here, I think looking at the right-hand side might be the best one. So I'll need the reaction at E. And you'll see now we have a challenge because I need EY, but I've also got a reaction at CY and a reaction at AY. Now when my unit load is here, what's my reaction at AY? Anybody know? Well, let's break it apart. So I'm going to break it apart into two structures, two free bodies. I'm going to separate it at the hinge. Why is that a good place? Because there's no moment. So on this side, I'll assume that there is a reaction BY and BX. And then on the other side, I'll have equal and opposite. And then I'll have the rest of the diagram as I drew before. With CY, EY, and my unit load. So what's this side look like? What are all the forces here? 0. There's no load there. So BX and BY are 0. And once you know that, how can I find EY with one equation? Sum the moments at C. Let me go ahead and write the dimensions here. 5, 5, and 10. So summing moments about C, what do I have? The unit load creates negative moment with the moment arm of 5 feet. And EY creates positive moment with the moment arm of 15 feet. Okay? So what's EY? 15 divided by 5, it's 3. It's got this weird unit. It's just feet, right? Oh, it's the other way around. It's 1/3. Sorry. I did the same thing somebody else did. Yeah, it should be 5 divided by 15. So now I can go back and find my internal moment at D by cutting it, put my value of EY on the structure, which is what? 1/3. Here's my positive moment at D. What is it equal to? Well, again, some moments at the cut this time. And what do you get? Well, with my sign convention, you get a minus. This is negative. The 1/3 is positive times a moment arm of 10 feet. So it looks like the moment at D is 5. Oh. Sorry. Let's see. One of them is positive. This one's positive. So it should be 10/3. So that means this value is 10/3. So what does that make this value? Negative 10/3. Why? 10/3 is to 5 as what is to 5? They're the same. So there's your influence line. So now we solve the problem with the concentrated load is 5 kips. So I have a concentrated I said 5, but I meant 4. It's 4 kips. So where do I put my concentrated 4 kip live force where it creates the maximum positive moment?
At 15 feet.
At 15 feet, it's here. So that means the moment at D from this would be 4 kips times 10/3 feet, which ends up as 40/3 kip feet. That's the moment, which is equal to, what is that, 13.33? Now, it also says there is a dead load of 200 pounds per foot. Now to do dead load, what do? We take the total area under the curve. So there are some negative sections and there are some positive sections. So I'm going to do them all. So I'm going to start off with my 200 pounds per foot load. Now all of these are triangles, so I'm going to put the 1/2 out in front. 1/2 base times height. So I'll start with the first triangle. It has a base of 10 and a height of minus 10/3. The second triangle has a base of 15 and a height of positive 10/3. So what's that equal to?
150 over 3.
Huh? Somebody calculate all that. This looks like 50 over 3 times 100, so that's 500 over 3.
That would be 26.
What's 500 divided by 3? 160 something? I don't know. This is pounds.
Wait, 150.
One. I don't know. Somebody calculate this. Don't you guys have a calculator? I don't have one. I'm thinking this part right here is 5 times 10, which is 50 over 3 times 100, is 5,000 over 3, which is 1,666.7. So that would be 1.67 kip feet. So you add the two together. So the moment at D, due to that combined load, would be these add together, which conveniently comes out to 15 kip feet. Right? 13.33 plus 1.67. Any questions about that?
Since there's also a uniform load,
We're not doing the uniform live load. We're not doing uniform live loads. That's beyond. We only have 7 minutes of our class left. Not enough time to worry about that. Okay, well, I'll stop that one then.